So let's start with this first optimization problem. We have an area of 6 square meters in a rectangular field. So I have some rectangular fields, and then I want to divide it in half with a fence parallel to one of the sides of the rectangle. So how can I minimize costs? So first of all, let's just assign some variables here. So we can call this, let's call this W for width. So we'll call this W, and then I'll call this L for length. My primary equation is what I'm trying to minimize or maximize, because eventually we want to take the derivative, and we know from the derivative we can find our max and min. So if I want to find the minimum cost, then I'm going to use that as my primary equation. So I want to use a cost equation for the primary equation. So whatever the length of the fence will be, will minimize the cost. So all we have to do to minimize the cost is to minimize the length of the fence, right? It doesn't matter what the cost is, as long as we minimize the length of the fence, that will minimize the cost. So we say that the cost, I can call this W also, and I could call this L. So if I sum up the size of the fence, I have 2L plus 3W, and again, if I minimize that, if I minimize the length of the fence, that will minimize the cost. Then I have my constraint, which is what am I restricted to? If I wanted to minimize costs, I could just say, why can't the cost of the fence just be 0? So I have to have a constraint. I have to restrict to the fact that the area of this whole field must be 6 meters squared, right? So I have to put a fence around that field such that the area is 6 meters squared, so I can't just choose an area of 2 meters squared and then find a smaller cost. I have to minimize it somehow. So I'm under the restriction that the area is 6 meters squared, and I know the area of a field or the rectangle is length times width. So we're going to use the fact that area equals length times width, but then I'm going to replace A, or the area, by 6. Step 2, what I'm going to do is I want to plug the constraint into the primary equation. So again, the reason why I want to set up that primary equation is I want to minimize or maximize it. So I want to eventually take the derivative of it. But I can't take the derivative of it yet because right now I have 2 different variables. And so what do I take the derivative with respect to? So I can't take the derivative yet. So what I'm going to do is I'm going to plug the constraint into the primary and reduce this primary equation down to just a function of one variable so that I can eventually take the derivative. Right? Because right now I have L and a W, so which one do I take the derivative with respect to? So what I'm going to do is I'm going to solve for L, or I could solve for W, either one, it doesn't matter, it's the same difficulty level. So here I'll just solve for L. Constraint is now L equals 6 over W. And then I'm going to plug that into the primary equation. So if I plug it into the primary equation, I have C equals 2 times 6 over W plus 3W. And that's going to give me C equals 12 over W plus 3W. And now I'm done with step 2. Step 3, now I go ahead and take the derivative of that because I just took a function with 2 variables and I converted it to a function of 1 variable so that now I could take the derivative of it because I know that will help me find my max or min, in this case the min. So now I go ahead and take the derivative of this. I have C prime. Number W is my variable, so I'm taking the derivative where W is my variable. So I have negative 12 over W squared plus 3. I set that equal to 0. Now I find when W makes this equation true. So I solve for W. I get 3 equals 12 over W squared, or W squared equals 4 when I cross multiply. And now I have that W equals plus or minus 2. Think about what we're doing here. We're trying to find the dimensions of a rectangular field. And so it's not possible for W to equal negative 2 because then the width of the field would be negative. So we have to reject the fact that W equals negative 2. So W equals 2 makes the derivative 0, which doesn't tell us that it's a minimum. All it does is tell us that it's a critical number. So remember that from section 4.1. So we don't know that it's a minimum yet. All that we know is that it's a critical number. If you stop there with your solution, it's not a full solution because we have to prove that it's a minimum. All you did up to this point was to just prove that it's a critical number, which doesn't tell you whether it's a max or min. So what we're going to do is we're going to prove that's a minimum by either the first derivative test or the second derivative test. I prefer the second derivative test for these, just because sometimes it's just easier to work with, but it's up to you. So I'm going to go ahead and do the second derivative test, which I'll just abbreviate as SDT. So there's my first derivative, right? So now I'm just going to take the derivative of that to get the second derivative. So I have C double prime equals negative 12 times negative 2 is 24 over W cubed plus 0. Now, using the second derivative test, I want to see if that's positive or negative at the critical number. Okay? Well, at the critical number, if I plug 2 in, I get 24 over 2 cubed, which is positive. Right? So we think about concave down as a sad face, concave up as a happy face. So here, if I have concave up, right, we're thinking about up being optimistic and happy, right? So if it's concave up, then that tells us here that we must have a min. If it ends up being concave down, meaning the second derivative is negative, then that would tell us we have a max. So this must be a min because it's concave up. We do have a min, okay? And so again, we just have to verify that. So we have a min, so that's great. So now the last step we have to do is just find the other dimension, because right now all we have is W. I need to find the dimensions of the field, so I have to find L. So step 4, find the dimensions of L. Well, how am I going to do that? From the two equations that I came up with, I want to plug it into the constraint, because the constraint is what I'm restricted to. So if I know that W equals 2, then I could just plug it into here to find L. So I plug it into the constraint, I get L equals 3, and some of the dimensions of the field are 2 by 3. So let's take a look at the next one. The next one, we have an open box, meaning there's no cover. We also know that it has a square base, has a surface area of 108 square inches. So it has a surface area of 108 square inches, meaning if I take the area of each side of the box and add them together, that's a surface area. And then now I want to find the maximum volume. So let's draw what this looks like. I'm not very good at drawing, so what I'm going to do is I'm going to take that box with a square base, and I'm going to tilt it on the side so that we could really see that that base is a square. So here is my drawing. So we have a square base. There's no cover, so the face that's opposite us that we can't see, there's nothing there, it's open. Again, we're tilting the box on the sides just to emphasize that we could really see that square base. And so if we have a square base, then we know that 2 of the dimensions of the box are the same, because it's usually length times width times height, but here, because the base has the same dimension on each side, then we can reduce that to only 2 types of dimensions, even though we have 3 dimensions. Okay, so we'll call this height right here, because again, we're tilting on the side, otherwise it would really be the height. And then if we want to call this something else, we could call it L for length, we could call it W for width. So let's just call it L. Okay, so I'll call this L. And then this is L also because we have a square. We could write it as L and W, but because we have a square base, we could just get rid of the W and replace it by L because we know that these 2 sides will be the same. Okay, so let's set up our equations. First, with the primary equation, again, we always want to think about what we're trying to minimize or maximize. So here I want to maximize volume, so that will be my primary equation. The volume of a box is typically length times width times height, but here, because I know that the width is being replaced by L, because the length and the width are the same, we could write it as length times height, or length squared times height. In other words, L squared times H. So again, we have volume equals L squared times H, and our constraint is what we're restricted to. Okay, because if I think about maximum volume, well, why can't I just find a box with a volume of 1 million, right? We have to have some kind of restriction here, and our restriction is the fact that the surface area must be 108. That's going to be our constraint, is the surface area. So we just have to figure out how to find the formula for surface area for this particular box. Let's think about the sides of this box. We have one side of the box with dimensions L by L, and the other 4 sides of the box we have with dimensions L by H, right? So we have 4 of those, and we only have one side with L by L because the other side is an open cover. So again, we have one side that's L by L, the other 4 sides are L by H, so when we calculate the area, well, if it's a square or rectangle, we just multiply those dimensions, so the area of the first side is L squared, the area of the second side is LH. And we have that times 4. So my constraint, again, is a surface area, which is 108, which again, surface area means we're going to take the area of each side and add them together. So we take the first side, which is a base, the L by L, which is an area of L squared, and then I'm going to add the area of the 4 sides together. So I have 4 sides times the area of each side, L times H, to get the surface area, L squared plus 4LH. Again, it's the sum of the area of each of the 5 sides. Area of the base plus the area of all 4 sides combined. That's why we're multiplying by 4, because the area of each side is LH, then we multiply by 4. Step 2, before we find the derivative of the primary equation to maximize volume, what we want to do is we have to reduce this to a function of just one variable, because right now we have both L and H. So I'm going to do the same thing as before. For the previous example, I'm going to either solve for L or solve for H, and then plug it into the primary equation so that we just have one variable. Now in the previous example, I said that the difficulty level is the same whether you solve for L or if you solve for W, but in this case, there is a significant difference in difficulty level. You wouldn't want to solve for L because we have an L squared and an L in the equation, so it would be very difficult to solve for L. On top of that, when you solve for L and you plug in here, now whatever you plug in, you have to square it, which could result in a lot of foiling and tedious calculation. So instead, if I solve for H, things will be much easier. So let's go ahead and solve for H. So I have H equals 108 minus L squared over 4L. And now I'm going to plug that into the primary equation. My primary equation becomes V equals L squared times 108 minus L squared over 4L. Now I simplify that. You could take the derivative from here and move on to step 3, but you wouldn't want to, right? Because looks like it's going to be complicated. We have to do product rule and we have to do quotient rule. So do yourself a favor and simplify the function first before you go ahead and take the derivative. So the L squared and the L cancel to just be L. So I have L over 4 times 108 minus L squared. Let's go ahead and simplify that a little bit further because right now if I were to take the derivative, I still have to go ahead and apply product rule. So let's avoid that. I'm going to just distribute this into both terms. Now we have 27L minus L cubed over 4. Now I'm ready to take the derivative because now I just have one variable. I take the derivative, 27 minus 3L squared over 4. I set that equal to 0, and now I solve for L. 3L squared over 4 equals 27. Now I get L squared equals 36. Now I go ahead and solve for L. It's just like the last problem, we know that the length of a box cannot be negative, so we reject the -6 and it's just L equals 6. Again, this is just the critical number. If this is all you have in your solution, it's not a full solution because again, all we did was find the critical number and then you're not demonstrating that you know the material because we didn't actually find that this produces a maximum. So to see if it produces a maximum, again, you could either do the first derivative test or second derivative test. So I'm going to go ahead and do the second derivative test here. I take the derivative of V prime, and I get -6 L over 4. And so when I plug in the critical number 6, and if it's negative, it's a sad face, because I have a concave down, right? So if the second derivative is negative, that means I have concave down, which gives me a sad face, so I know I have a maximum. So that verifies that I have a max. Last step here, step 4, is to find the dimensions, right? I know that L equals 6, so now I just have to find the other dimensions. I know that the base is L by L, so the dimension of 6 is going to show up twice. Once for the length and once for the width. So I have L by L, and then my last dimension is H. So again, I'm going to plug it into the constraint and plug L equals 6 into the constraint and solve for H. So again, I plug L equals 6 into the constraint, I solve for H, and I get H equals 3. So we have 6 by 6 by 3, because again, I used that dimension L twice. Once for the length and once for the width, because I had a square base. So when I ask for the dimensions, make sure you write it as dimensions, right? I want to know, is the 6 being repeated or is it 3? So just make sure to indicate that. Okay, so I already did the third example in class, which was a distance one, so I'll go ahead and skip that. So let's go to the fourth example. For the last two examples, the fourth and fifth example, I'm just going to show you how to set up the equations. That's when students typically struggle, is with setting up the equations, and then you can try the rest of the problem on your own. The solution to the rest of the problem is on Canvas, so if you just go to the lecture materials section on Canvas, the rest of the problem is there. So I'll just set up, you try the rest on your own, and then you can check it with the notes on Canvas, and then let me know if you have any questions. So setting this up, we know that we're given here that the wire costs $3 per meter. We have a $200 budget, and we want to find what would give us the largest area of this field if this field is bounded by a river on one side. Okay, so I have a rectangle here, so let's just call this L and W. So let's go ahead and set up a primary equation constraint. Again, our primary equation is what we're trying to minimize or maximize. Here we're trying to find the largest area, so the area formula is going to be my primary equation. So yes, this doesn't really look like a rectangle because of the way I drew the river, but just assume that the river is forming a straight line. Okay, so maybe just think about it like this. And then the area would just be length times width. For the constraint, well, if I'm trying to find the largest possible area, I can't just choose the largest area that I want to. I'm restricted to the fact that I have a $200 budget, right? So around that area is a fence, and I have to build a fence that I only have $200 to work with. Right, and the fence costs $3 per meter. My restriction is the cost, right? So I have a total of $200. If it's $3 per meter, then when I multiply $3 by the total length of the fence, I should not be more than $200. So my restriction is $200, and I can find how much I'm actually paying for the fence by multiplying $3 by the total length of the fence. So my constraint is $200 equals 3 times the total length of the fence, right? So my restriction is $200. I have $3 per meter, and then times the total length of the fence is W plus L, or 2W plus L. So that's how you would set up the primary equation constraint. Again, you can try the rest of the problem on your own. The next step would be either solve for a W or solve for L. Looks like it's about the same difficulty level in this case, so either way, plug it into the primary equation and then continue from there. Again, the solution is on Canvas, so you could see the rest of it. Let's go ahead and do the last example. Again, all we're going to do is set up the equations for the primary equation and the constraint, and then you could try the rest on your own. So I have a box with an open top, right? So there's no cover. So we have no cover on the box. And then we have a volume of 15 meters cubed. We have the base. The length of the base is 3 times the width. We have $2 per meter squared, the cost of the base. And then the sides are $5 per meter squared. Okay, so let's go ahead and define this let's define dimensions here. So we'll call this the height. Right, so I'll just label this as H. I also know that the length is 3 times the width. So what I could do is I could label one of the sides as the width, okay? Not necessarily drawn a scale here, so don't think about it too much. Let's call this the width. And if the length is 3 times it, instead of labeling it as L, why not just label it as 3W to get rid of one of the variables so that we don't have too many variables to work with. Otherwise, we can't solve. So now we only have two variables to work with, and I know that when I take the derivative, I could plug the constraint into the primary and reduce it to just one variable. If I had L here, then I would have too many variables, right? So now, if I only have two variables, I could reduce it to one variable by plugging the constraint into the primary. So my primary equation, again, is always what I want to minimize or maximize. Here, I want to minimize cost, so the cost equation is going to be my primary equation. Well, the cost will just be the amount of money per meter squared times the area of each side, right? If I'm saying that it costs $2 per meter squared, then that means I could multiply $2 times the area of the base, and that will give me the cost of the base. My base has dimensions 3W by W, so to find the area of the base, I have 3W times W, which is 3W squared. The cost of the base is $2 per meter squared, so to find the total cost of the base, I could multiply the area by the cost per meter squared, and then I get the total cost. 3W squared times 2 is 6W squared. That's the total cost of the base. Now to find the area of the sides, notice here that there's two different sizes for the sides. We have this side and then we have this side. So I'll just do these separately. We have two sides with this side A, and then we have two sides with this side B, right? So we have to treat them separately. So my side A has dimensions 3W by H, right? Because this H is the same as this H. So the dimensions of side A is 3W by H. So the area, I just multiply those dimensions together to get an area of 3WH. The cost of this side, as given to us, is $5 per meter squared. So to find the total cost of one side, I multiply the area by the cost. And so here, I get 3WH times 5 is 15WH. Notice here that there's two of them because there's a side A that's facing towards us, and then there's the one behind that, right, that's parallel to it. So there's two of those. And lastly, we do side B. Side B has dimension W by H. We calculate the area, which is WH. The cost of each side is $5 per meter squared. So when I find the total cost of one side B, I multiply WH times 5, and I get the total cost. And again, there's two of these as well. So finally, to find the total cost of this whole entire box, we take one total cost of the base, we take the total cost of side A and multiply by 2, because there's two side A's, and then we take the total cost of side B and multiply that by 2, because there's two side B's, there's one that we could see, and then there's the other that's parallel to it. So combining all that, we get the cost equals 6W squared, which is the base, plus 2 times the total cost of side A, because again, we multiplied by 2 because there's two of them, 15WH, plus 2 times the cost of side B, because again, there's two side B's, WH times 5. So simplifying that gives this, okay, and that's the primary equation, that's the cost. Again, we take the total cost of the base plus 2 times the total cost of side A plus 2 times the total cost of side B. And remember, there's no cover, so that's why we don't multiply the base by 2. It's just one of them. Now I go ahead and find my constraint. My constraint is what I'm restricted to. I'm restricted to the fact that the volume is 15 meters cubed. Well, volume here, okay, is just multiplying the three dimensions together. So volume equals not length times width times height, because that's not what the dimensions are here. It's 3W times H. So we have 3W times H, because instead of length times width times height, the L is being replaced by 3W. So the constraint is V equals 3W squared times H, but I replace that V by the volume, which is 15. And that's our constraint. We're restricted to the fact that the volume must equal 15, right? So the constraint, we plug in some value because that's what we're restricted to. We're restricted to the volume being 15, but for the primary equation, we don't plug in the cost because that's ultimately what we're trying to find. We're trying to find what will give us the minimum cost. Again, the rest of this problem is on Canvas. If you just look at the notes in the lecture material section, try the rest of the part on your own first to make sure you can solve, and then check your answer on Canvas. And let me know if you have any questions.